Hello everybody, can you hear me? So today I'm going to talk about CFG-based fuzzy hashing for malware classification. So it's a topic, malware classification is a topic by itself. It's mainly aimed to be able for a malware analyst to classify a malware, a new malware sample he just got, to be able to tell if it's from one family or another. So who are we, or more exactly who I am? So I am Robin Marcelier. I was supposed originally to give the talk with Lancelot Bogart. Unfortunately, he couldn't make it to Barcelona. So I'm gonna try to give the presentation by myself only. I'm not a reverser. He's more the reverser. Lancelot is more the reverser of us. He was supposed to give the most technical part, so I'm gonna try to do it by myself. So, why CFG-based classification? Apparently, it's used by antiviruses for as a kind of last resort to be able for them to tell if a sample is malicious or not. It's also used by academics and some other entities to do some research, to conduct some research on malwares. But yet, I couldn't find any public implementation very easy to use and very easy to deploy at large to be able to classify malware at large. So we tried it. We tried to do our own. We did find one, though. We did find one, but I'll talk about it later. So the main objective of this CFG-based fuzzy hashing is to get something better than MD5 and the SHA family to be able to classify malware. So it's not really hard because MD5 and the SHA family are mainly used in malware research to be able to identify malware only, to know if this sample is a particular, if this sample only. We try to do something also better than the SSDeep, which is another fuzzy hash for malware. We try to do something better because SSDeep is not very old, but it's a bit old now, and it's quite easy and to be able to produce different sample from the same source code with different SSDeep signature. The main objective was to produce a small and independent tool as much as possible, which is very easy to deploy and use at large, and let other tools do the clustering. By clustering, we mean the ability to regroup a sample inside a family of malware. So we do find another implementation of CFG-based fuzzy hashing inside a project named Polychambre from ANSI. So this is published on GitHub. You can find it very easily. There is inside Polychambre there is two implementations of the algorithm named machoke. It's one implementation is in Ruby, the other one is in IDA Python. And the two implementations are lost in lots of Ruby and Python and other sort of languages, including Perl. So it was not very easy to use at large. So that's why we try to re-implement something else. So we named our project machoke because machoke, the original. This one, the original, was the name given by ANSI. They just choose the name of a Pokemon, and we just choose for our name the evolution of this very Pokemon. So, quite simple. We used radar and radar 2 and r2 pipe to do our stuff along with Python. And now I'm going to explain the algorithm more clearly. So this is the control flow graph of a function as given by a radar. So basically, we can see different code blocks. So the first step to be able to extract a hash from this is to label the blocks and the calls. We are only using the blocks and the call as for our fuzzy hash. So we just give a number to every code block, and we see that there is a course here. After that, we translate it to text. So basically, we can see that the first code blocks is only jumping to the second one. So we translate it by the beginning of the string there. Afterwards, we can see that there is. Oh shit. After this, we can see that the block 2 is calling either 3 or 4. So we translate it to the string. The next block 3 is either doing a call or jumping to 2. So we translate it that way. And the same for the fourth block, which is only returning. So it's not jumping nor calling anything. From that, we generate a memory hash of the string. So to keep the why memory hash, it's because it's not a hash algorithm like MD5 and SHA. On the SHA family, there is no avalanche effect. If you modify only the end of the string, the memory hash is not going to change entirely. So it's quite efficient for what we are trying to do. And after that, we repeat this algorithm, this small algorithm for every function in the sample, in the binary. And we then concatenate the hash. So the main consequence of this algorithm is that it depends on the number of functions of the hash. So the bigger the number of functions of the sample, the bigger the hash is. So it could be problematic in some case with very big binaries, but usually malware samples are not, so it's good. For this, we used a very few commands inside radar and R2pipe, mostly AA to analyze. The second one to get some information about the binary. The third one, AFLG, to produce a JSON listing the functions, to be able to iterate over them using the fourth one. That's giving us the contour, the CFG graph of the function. So the results. We did the first analysis on a small collection of samples. We classified by error rules. So there was more than 20,000 samples, and then more than 20,000 MD5 and SHA, as expected. We did the same with SSDeep to see what to have a kind of reference, and we found half the 10,000 basically. And when we did it with our algorithm machoke, it was less than 5,000. So it was quite promising as a way to classify malwares. So we can see that at least 15,000 malware are related to any other. We did a second analysis on the banana user per tool family leaked by the shadow broker. So basically, we had 80 different samples we knew from the same family, and there was only 3 different machoke for all of them. So it's quite promising actually. In the future, we plan to add the ability to perform a machoke hash for functions only of malware. Actually, we are only performing machoke hash for the whole sample. We probably will do it for a function as well. And we will mainly try to integrate machoke inside other tools, mostly MISP and Viper. And if we can do it, build correlation and clusterization tool on top of it. The code is not yet public. We suffer a little delay, so it's going to be public within a few days at this address. That's all. So if you have any question. Yeah. I can't hear you, sorry.
Okay.
Yeah.
So I'm curious if you correlate parts of your hash. So you showed kind of interesting approach, but then if there is a partial correlation, do you do this correlation?
I can't. I don't get it.
So if you have a hash,
Yeah.
and you have this hash represents the structure of your
Yeah.
sample, but there could be a partial correlation in the hash. So it's not the whole hash, but there is a partial overlap.
Yeah.
Do you do this correlation? Like if you compare samples, you just compare each and every syllable there, or you can find partial correlation, like 80%, 40%?
Actually, we didn't try to do it yet. We just tried to find a direct correlation, like the exact same hash. But the hash is built in a way that this can be done. But in my opinion, this kind of job is not to be done inside this tool. It's up to another tool to do it, like
yeah, clustering.
Yeah,
okay.
exactly. Clustering is up to another tool, so and it's quite a mathematical problem. So we just did this part so far, and we let maybe other people do the clustering using the proper mathematics and the proper algorithm. So there is a question here.
Will it be possible to use it for whitelisting approach? Like we just do it for all Windows binaries and
it would be possible in theory, I'd say, but the hashes would be quite huge because they depend on the number of functions of the binary. So it might be possible, but I'm not sure it would be very easy and good for performances.
Thank you.
You're welcome.
Any other question?
There is two.
Hello. Have you tried this tool against samples packed with auto-eat, for example?
We've tried it quickly. The packed samples are a recurrent question with the CFG graph. My initial expectation was that it would be possible to recognize the packer directly from the produced hash. It seems that it's not that easy, so we are still working on this topic.
No. I mean, the malware authors, they can create malware by using some tools like auto-eat, PyInstaller, and so on.
I don't get the point.
So you have I don't know, 100 executables.
Yeah.
Some of them are malicious, some of them are not, and all of them are created by same tool like auto-eat.
Okay. Yeah, for this we don't have an answer there yet. I don't know what would be the result for this. We don't tried it.
Anyone else? Okay.